So, hi, I'm Jim Sluka. I'm a senior scientist at Biocomplexity Institute in the Intelligent Systems Engineering Department at IU. I've been working with James for almost 13 years now. We're going to talk today about some general stuff about handling files from CompuCell. Capability CompuCell has called parameter scanning, or PSCAN, lets you automatically scan parameters in a simulation. And then hopefully, if we have some time, some best practices stuff at the very end. Reminder that this is being live streamed and recorded and will be distributed. Post your questions and such to the chat, and Hayden or somebody can yell at me to stop if there's a question that I don't see. Okay, so as I say, we're going to talk a little bit about writing the files, the parameter scan, and some parameter files and other best practices. This deck used to have sensitivity analysis in it, but that's gone. Well, there's no way we'll get that far through. Okay, so start off with writing data to files. You can always just use standard Python tools for reading and writing to files. Sometimes that's the best way to do it. But CompuCell does have some helpers in Twedit to help you do certain things. And CompuCell also has internal knowledge about where it's writing its default simulation output directory. And it's nice to be able to access that directory as well. So as I say, so Twedit has some built-in templates to help you. The typical process is you would open the file in the start method, write to the file in the step method, and then close the file and finish. The demo we'll be using is called writing to files base. And when we're done, we're going to have a CompuCell project similar to the file writing to files. So the one on the left doesn't have what we're going to do in it yet, and the one on the right has everything in it already. So if you ever fall behind and you just want to jump ahead to a solution, you can open up the other one. So the writing to files base is just a real simple cell sorting simulation. It only runs for a few hundred MCS, so it doesn't actually sort very well, but we just want something that we can use as a template for reading and writing to files. So to get started, let me change my screen share. If you get into the demos folder and find that writing to files base file, and I'm going to share this. All right, so hopefully now you can still see my PowerPoint deck. And can you also see my Twedit window?
Looks good.
Yep. Thank you. Okay, so normal CompuCell stuff. I actually have had the file open recently. So it's still in there. So like I say, this is super simple. It's got A cells and B cells, and it makes a field of them and assigns everybody the same J value and runs some steps. What we're going to do is we're going to convert this into writing some information to a file. So the first way of doing it uses a Twedit helper, and it writes to the standard output directory. So that's the folder that you get every time you do a CompuCell simulation inside of your workspace directory. So CompuCell knows about that folder. So we'll go to back over here to Twedit, and we're going to open the file. So let's do that in the start. Make some room for it, and then it's in CC3D Python. CC3D Python, and then the Python utilities, and then open file and simulation output directory. So that's your workspace directory that's going to be created with your file name and your timestamp and everything else on it. So CompuCell has a little helper for that, and it inserts this little piece of code, and it indented it too far, so I'll pop it back out a little bit. So this returns this call to cell file open in simulation output folder returns two things: a file object, which is the pointer that you use to refer to the file, and the file path, which is, as the name implies, the object or the path, the Unix, Windows, or Mac path to the file. It has two arguments: a file name and a mode. Let me switch back over to here. So we want to do something like give it a file name to actually open, and we want to do something with the mode. The available modes are, happens to be standard OS type stuff. You can R for read, W for write, and A for append. If you use A for append, it opens the file if it exists and starts adding to it. If it doesn't exist, it will create it without throwing an error. So what we want to do is we want to give it a file name, and you can put the file name in a variable if you want, or you could just enter some useful file name like logfile.txt. Now we got the file open. Now, since we're doing this in the start, these two variables are not accessible to anybody else. Not available in the step or in the finish or on the stop functions. If you want everybody to be able to see those, you can just add self in front of them. Now all of our other modules have access to this object. The next thing we want to do is this. Notice this again. This is the code that the Tweedit helper inserted. The next line there says file object is none, return. That's basically an error state. It says it tried to open the file and couldn't, so the file object is empty. Now actually it'd be self file object. But the snippet says that's fine. Just ignore it, and that's not a good idea. The worst thing that can happen is you open a file and it fails in the start, and then you're on a 12-hour simulation and you find out that you can't write the file because it failed at the start. So we'll want to change that a little bit. And here in the slides is what we're going to do. Basically what we're going to say is it'd be nice to write a message, but the bottom line is you just want to bail out. You can't open the file, don't do anything else, just quit. And like I say, it'd be nice to say, give an error message. Spelling doesn't matter in computer programming. Couldn't open the file, can't have that guy there. And exit. Okay, so we got a file open, we got a file handle to it, and we're sure that it actually opened successfully. Otherwise, Compsol would have stopped running. You want to write to the file. It's your file object name, the same name as you have up here, .write, and then a text string. It'll put that into the file. By default, the write method doesn't include a line break at the end of its writes, unlike a print statement in Python. So you need to throw a line break in there if you want a line. You probably do. Okay, so now we got our file open. And that's an example of writing some stuff. We can use that in our steppable. We have a little line here that every 50 MCS, it's going to count how many cells of each type we have. So this just uses that list that you've probably seen before when you want Compsol to iterate over all cells of a particular type. Well, you can just use that list with the len function and get how many cells of that type you have. If we do that, we get how many A cells do we have, how many B cells do we have. We then build an output string that's a little tag, and then the count of A cells and the count of B cells. Notice I put strings around this. For a print statement, you wouldn't need that, but for writing files, you do. You have to convert everything that looks even remotely like a number has to be converted to a pure string. And then finally, we're going to write again. Here's our self file object write, but we're not going to write top of file. We're going to write our output. Type weren't too bad. So every 50 MCS, we're going to write a count of A and B cell lengths, vectors lengths. And this command also has its line break at the end. Finally, we want to close. We want our finish. and it just close. It isn't strictly required. CompuCell, Python in general will close the files when the execution finishes anyway, but it is nice to close it formally. It also gives you a chance to write a closing message or something to your file. On stop usually calls finish. I think this would do it to ensure that the file gets closed, even though, again, it's really not strictly required. Okay, so this is going to be writing to the project folder. We'll save it. And let's see if it works. See how many errors I typed in. Okay, it ran and it's done. Like I said, I'm only doing a few steps. Now let's see if we can go find that output. So here's my workspace folder. Here's the simulation we just ran. And in that folder, there's the logfile.txt that we wrote. And if I open up logfile.txt, that's what it says. So apparently, I got a bug there. So I didn't want to write output text. I wanted to write the string. This string here is what I was trying to write. So save that. Player spin that out really, really quick. Let's go up a directory. Now we have a new output directory. Go down to there, go into log file. There we go. So we only did 100 MCS, so we only got one report. So there were 163 A cells and 321 B cells. Okay, so that's straightforward. That's putting all your output into your workspace, which sometimes you want to do. I find more often than not, though, instead, what I want to do is I want to write back to the project's directory itself instead of into the workspace. And I want to track stuff, and I want to keep adding stuff to the file. So I want to append to the file. If you're writing to the workspace file, it doesn't really make much sense to open it and append to it because it won't exist. And when you finish the simulation, you'll be in another directory the next time you run the CompuCell again. So if you're writing to the workspace, appending it doesn't make too much sense. If you're writing in the projects directory, it makes much more sense to append to a file. So we'll do that. We'll just go ahead and add that into what we've already done. We'll use the same demo. CompuCell has, now we need two helpers in Twedit. One is to get the current directory that we're working from. And the other is import OS, which is a generic Python package for handling things related to the operating system. So again, we're going to open it up here in our start. So we'll come up here back to our start. And again, it's CC3 Python utilities, import OS. It just sticks import OS in there for you. Again, CC Python utilities. Get full path of the current file, or get dir of the current file. So file dir now contains the path to my project itself, not to my workspace, but to my project itself. Oddly, this actually points at the parameter file, the parameter directory. So you could write the file there, or you can move up a level. And you can use the OS package to do that. This command here basically is just dir name, and that moves you up one directory. So now file dir is the parent directory of file dir. Then that's the directory path. So it's not actually a file name. So we'll make a file name by joining that upper level, that up one level directory with a file name logfile.txt. So all of that was just to figure out where we're at and create a file name. And finally, we're going to just use generic old Python to write to the file. So just like I said, this is the generic open for Python, our file name that we just created. And it uses the same syntax as the Twedit helper did. At A is append. You also have W for write and R for read. And we write to it just with the file handle .write and then a string. So start of the log file. And now we can do the same thing and write our data down here. And we should close our file too. Okay, so now we have some code up here, import the OS, make a new file name and move the directory up one level. And then in our step, we'll build an output string and actually write it to our output file, append it to our output file. And then the finish, we'll close our files. Again, we're using the self tag all the way through so that all the other parts of the steppable have access to that file name handle. Save that, open the player. Already done. Let's see if I get any error messages. No, I did not. The run took 2.5 seconds. And if we go back to the workspace directory, we still have our log file. That log file. But now in our parent directory where we're running from, it should be here. So this is my working directory. Now I have my other log file 2. And it's got the same data. I was writing the same data to both places. Now, if I keep that file there and come back here to CompCell and go run again, excuse me, that's not CompCell, this is CompCell. Bang, 2.5 seconds, it's done. Says this file has been changed. You want to open it? Say yes, okay. Now it's been appended to it. So every time I run CompCell, it'll just keep adding onto this file. Very handy, great way to keep track of stuff. You can print your parameters. You can put a timestamp in if you just want to make sure you're keeping track of what date you actually ran it. You can do, anything else that you think is worth saving. Usually you'd be saving things like parameters and some metric of how well your simulation worked. In cell sorting simulation, you might calculate the surface area between the condensing cell and the media. A really good sort, there'd be no surface area contact between condensing and media. So at the end of your simulation, and maybe your finish, you'd calculate that metric and write it to your file, maybe with your J values or whatever else you thought was relevant to save. So again, the summary, open it and start, include self, write something in your step as many times as you want. On stop and in finish, you can write a close message and then make sure you actually close the file. This is just a little snippet of Python for writing its timestamp to a file. You import a module called datetime. And if you print datetime, it gives this. So that's a great thing to put into your log file. Or you can name your log file that, though you have to be careful about some of these funny characters like dashes and colons. So if you've got a CompCell project handy, or using the one I was just doing, take a minute and see if you can write to a file real quick Uh, let's see, I lost my chat. Where did the chat go? There it is. Okay, some questions in the chat. Yep, somebody got Sharon caught my error before I before I found that. Yes, Sharon was right. Interrupting, yes, it's possible. You can import any Python package you want. If it's not in the standard Python installed, you may have to go to Conda, install that package in the Compsel work area. But absolutely, if you like pathlib or some other package, go and get it. If you want to do some other manipulation, you want to use k-means clustering or something, and you want to import the sidelib package or NumPy or something else in order to do that, you can do that as well. But yeah, whatever you're comfortable with. You could also import the JSON package and write a JSON format file, or the CSV package, which just a little bit of helpers to help you write comma separated and tab separated files. From Alina, yes, absolutely. You could save up all your data. One thing I kind of like to do is make a global variable or self.lineout. And in the steppable, I just keep adding stuff into lineout. And it just builds up a big text string. And at the end, you dump that text string into your output file. So whatever seems to work best for you, depends on how complex your data is and how much stuff you're writing. The nice thing about actually writing to the file in the steppable directly or in the step function directly is if your simulation crashes partway through, you've got stuff in the file. If you save everything to write when you finish, crash halfway through, nothing gets written to your output. You'd be surprised. Yeah, worrying about how much RAM if you're collecting everything into a string. If you're just writing text, a gigabyte of text is a lot of text. That's the Encyclopedia Britannica. An encyclopedia doesn't have a gigabyte of text in it. So that's a lot of data. I don't think you're going to run into that limit. And if you're writing a gigabyte of data to a file, you're also going to run out of disk space faster than you're going to run out of space in Python itself. Anyway, yeah, so whatever is comfortable. Like I say, a good thing to keep in mind is open the file early so that if it crashes, you know it, and you're not wasting much time doing a run and then finding out at the very end that you couldn't open your output file. And usually fixing bugs with output files that's a common problem to have, that there's just something wrong with your path. Both of the methods we just showed are location independent. So we didn't have any hard-coded paths in there. So if you take my code and put it on your computer, it should run exactly the same way. Even though your project folder will be in a different place, and even though your workspace is on a different drive, might be on a different drive than C drive. Okay, and there's a nice hint there that you can make a nice file name from timestamp. The other thing you can do is, remember when we use the twedit helper, it has the file path to the workspace directory. Print that. I did an output log or in the console log. Let's finish. Lost where it was at. There it is. So that output path has that. You could take this apart and pull out this part of the name, which is your base file name, your base project name, month, day, year, hour, minute, second. So that would be another way of getting a timestamp if you wanted to write into your log file. You could just use the file name that the default tool creates. Okay, I hope somebody, if you had time to give it a try. 15 encyclopedias worth test output over and over. Yep. Yeah. Write it every MCS and then do 100,000 MCS. Okay, so we'll move on. I think if everybody's okay with that, you can always pull the slides up for little hints and things if you forget the details. The Twedit helpers usually kind of help. And of course, you can always just use Google, Python, file open, file write, file close. Okay, next thing, parameter scans. So a parameter scan is a systematic and automatic way of running simulations as you change parameters. Parameters are changed in an orderly fashion. And it's a great way for exploring parameter space. The biggest challenge actually in parameter scanning is that this problem here of the number of simulations explodes very easily. You'd think, well, I got 10 parameters. Let's do 10 values of each of these 10 parameters. Well, that's a lot of simulations. And even with 10 parameters for just 5 values, so 10 parameters over 5 values, that's a 10-digit base 5 number. So that's 9.8 million simulations to do 10 parameters. Cell sorting, you have 5 or 6 J values, and cell adhesion actually interferes with target volume and target surface and lambda volume and lambda surface. So we're already up to 5 or 6 or 7 parameters just doing a very simple cell sort. So like I say, it's very easy to have this get out of control. And you kind of have to think about that when you start up that, you could do thousands of simulations. Hundreds of thousands of simulations are going to be a challenge unless you have access to a, 2,000 node compute cluster or something like that. But so it's something to think about going in. How many parameters you're going to scan, how many values for each parameters, how many simulations is that? And of course, if you're going to do thousands of simulations, you may generate an awful lot of output. Taking screenshots, and you're taking a screenshot every 50 MCS, and you're doing 50,000 MCS. So you've got a couple of hundred images in every folder, and then you're going to do 10,000 simulations. So you have to think about your output as well. How long is it going to take because of how many simulations, and how much output is this going to generate when it's done? So you might only want to save very few screenshots. And then the last thing that I left off this slide is the other thing you want to think about at the very beginning is, what are you going to save? What information about each simulation are you going to save? Screenshots are fine. Some metric that you calculate at the end of the simulation is probably going to be more useful, some numerical result. How are you going to save that? What value are you going to save? How are you going to calculate it? How are you going to save it? And how are you going to keep that value coupled to the simulations you did? So here's my output metric. Well, what were the input parameters that you ran in the model to get that output? So those are all the things you need to think about. Don't let it explode for too many simulations. Don't let the amount of data you generate get too big. And finally, think before you start about what you're going to save. What's characteristic? What are you trying to actually learn about? And how are you going to save that information along with the parameters you're actually doing? So moving on a little bit. Adding a parameter scan is a major change in the code. It's once you put it in, it's hard to get it back out again. It can be done, but it's It's a lot of work to get it out. It's more work getting a parameter scan out of a simulation than it is getting it in. So before you do the parameter scan, make sure everything works. Make sure you get all the bugs worked out, all the kinks. If you're saving screenshots, make sure you've clicked on the camera button, because once you convert it into the parameter scan, you're going to have a lot of trouble changing screenshot output. So the best way to do it is just fork your project. Wonderful way of doing it. Just make a copy and give it a new name. Okay, now we're going to start with a different example. Let me get rid of some stuff here. So this is in the demos folder. Excuse me. Let's see if I can open that up. Close this project. Sure I get the right one. Output base, this one. So this does not have a parameter scan in it yet. This is just this is basically the same self-sorting simulation. Little tiny simulation. It's going to do a few more steps than before. The other thing that's already been added in this starting point is there's an analysis and log steppable. And what it does is it writes to it opens some output files and writes some information there. It also writes to the screen and various other things. And it also, so it opens those files. It also makes an output metric. It calculates every 50 MCS the ratio or the total surface area between condensing cells and all other cell types. So it's the same thing here on this slide that's calculating that metric. This demo also plots it. So I can get CompuCell to start up. So simple cell sort. It's going a little bit longer than the one we've done for writing to files. And this is a plot of that, the heterocontact area for the condensing cells, which are the blue ones. The simulation is not running long enough to actually get a good cell sort, but it's definitely reducing the contact area for the condensing cells. So that's kind of our starting simulation. And our metric that we're going to log is that value that was being plotted. That's this is how good the simulation works. It's this number, and we're trying to make that number smaller and smaller. Okay, so this is self-sorting. Makes sense that we're going to explore the adhesion energies. We won't do all of them because there's too many of them. There's 6 of them. I'll only do a couple of them and only do a few values for each one. So I'm going to skip some slides and come down here. So we already saw that. This is what the starting simulation looks like. There's a little hint here about this is always a good idea in your number of steps in the pots. Always add 1 to it. Well, you do a whole bunch of stuff about every 10 MCS, do this. Every 500 MCS, save a screenshot. The problem is you don't know how those get called and in what order they get called when you hit the last MCS. And a lot of times your last thing won't get called because CompuCell orderly shuts down before it's finished doing everything that last step. So if you add that 1 there, you're always certain that you got the last thing done. And you're just going to blow away this 1 extra step. But anyway, very good idea to make sure you get that last step in. Okay, so like I said, the easiest way to add the project to it is you take your original file and or folder for your entire project, copy it, and then rename it. So my output base, make a copy of it, rename it to pscan or something useful instead of leaving it as named as being copy. But that's the best way to do it. That way you have your original unmodified file and your new pscan file. Okay, so the basic process, it's actually, like I say, it's actually pretty easy to add a pscan to a file. It's hard to get rid of it, but it's really easy to add it. And the process is you right-click over here in the file menu, and it gives you a pop-up, and there's an option to add a parameter scan. Select that option. That adds a new file into your CC3D set. So it's listed in the .cc3d file, and it's in your simulation folder. You can open this up, open up the parameter scan, and take a look at it. And when you first insert it, there's nothing really in it. We haven't told it to do anything yet, but that's what the whole process of creating it. So like I say, it's really straightforward. It's just right click over here in the file menu, add parameter scan. I have to open up so I can double click, and there's my parameter scanner. When I save, that's now a permanent part. If I reopen this project, that parameter scan extra file is in there. Okay, so that's how you add in the kind of the framework for the parameter scan. To actually add a value to the parameter scan, you just select it in whatever file you're interested in. So here I'm showing adding the medium to condensing J value. You highlight it and you right click on it, and you get a pop-up that says add to scan. And here is the details there, but we'll do it over here. This is this one. So you highlight it and then right click, add to scan. It wants a name. Since this is a J value, we'll just name it for what it is. It's the J value for between medium and condensing. Wants a start value, so original value is 10, so you might go 8. Well, actually, let's do a little farther. Let's do 5, 15, and we'll tell it 3 steps. And you have a choice of log or linear or random. You also have a choice of whether it's a floating point or an int or a string. These are actually floats, though int would probably work. And linear is fine. Click on the generate button. It says those are the values it's going to do, 8, 11, 15. This was supposed to have been 5. I can't type. Generate. There, now 5, 10, 15. And hit. Okay. You'll always get this error message because like basically an external process just changed one of your files, but that's fine. So yes. Couple of times. And now we have, here's the tag we used, the original value, and the values it's going to scan. The more important thing, though, is back here where I did it, I now have this instead of my original value. This is the flag. This is the flag that sets where it's going to write the values. Can I zoom in? How's that? Is that a little bit better? So just to recapitulate, in fact, we'll go ahead and do the other ones. This is, let's do this one. Highlight it, right click, add to scan, give it a name. So this pop-up dialog is what's hard to see. This is JCC. I'll do the same thing. We'll go 5 and 3. 5 to 15. Start minimum is 5, max 15. Generate 3 values. Okay. Messages again twice. Now we got JCC over here in our JSON spec for the parameter scan. And back here we got those guys. So you just keep doing that until you got everything added in you want. Now I was just doing the XML file. You can also do it in the Python. So I can go over to my Python file and find some value like cell target volume and say, I want to scan that. Now, again, just as in the XML, it's the value that you highlight, not the parameter name or not the variable name, but the value you want to change, because that's what's actually going to get replaced. Going add to scan. This is target volume. Give it a nice descriptive name, PV. Let's do 15 to 30. two-step generate. So now I've added that to it. Now back in my Python, it's been curly bracket replaced with the curly brackets and the value I'm using. So you do that in any one of your files. At runtime, those values get replaced. Now, like I said earlier, you're doing a parameter scan. You want to actually keep track of what's happening. So you want to log your result metric, but you also would like to log your parameter values. The nice thing about this tag and all of these tags is you can put that tag anywhere you want, and it will get replaced at runtime. So when the pscan routine replaces this one, it'll replace this one as well, and it'll print my TV value. So that means it makes it relatively easy to log all those values. So down here, it was already writing some stuff. It was writing the header surface area and the runtime and a few other things, but we can change that to add those values. Now I'm gonna have to go get what they were because I don't remember what they were. So that's one. And so it's going to be that value, a tab. This is just building an output line. We're going to write this value, place, and then we had one in here, this value. I have a header line. It's going to be wrong, but that's okay. Extra header, I'm just getting rid of it. Okay. Now I may need strings around this, so I'm going to go ahead and put those in just to be safe. That's there. That might work. We'll see. So recapitulate the process is right click over here, add parameter scan, go through your Python, your XML, any other file you want to go through and pick variable or values that you want to scan and add them to the scan. Think about and figure out how you're going to log. And in this case, it would be great to log the actual value used for the run plus our metric. In this case, our hetero contact area. Okay, so we got hopefully everything in there. We got all things added. We got an output statement, which is pretty iffy right now. It may or may not work. I'm sure I messed it up somewhere. So we're getting close. There's some slides here talking about, so you can edit the JSON file if you want. There's some no final comment. You can add things to it, values to it, or remove values. Just being careful. You have to be very careful of getting the syntax right. Okay, so now when I save this project, if you go and look, the .cc3D file now has another line added to it. That's the parameter scan file. If you look in your simulation folder, you've also got a new file called parameter scan spec.json. So you've added new things into the project. So finally, after all that work, we're ready to try and do a run. Now, remember, we're presumably going to be launching multiple runs. Right now, I think we have 3 and 3 and 2. So 18 simulations. If I've got a bug, it's going to run 18 simulations that crash. So we'll find out. So we're ready to run. How do we run? So run it the same way you do it any other time. We tell it open in player. And it hid the window. It's supposed to pop up this window, but it hid it between all my other windows. This you probably can't see, huh? And I can't change, I don't think I can change the size of a dialog window. So I'll walk through it real quick. So parameter scan simulation, and it just gives the big, long, ugly path to my input file. This is just where I'm at right now. It asks for an output directory, and by default, it'll be writing it into your workspace, and that's the default location is perfectly fine. You have the option to turn on output screenshots, a checkbox, and a frequency. However, this won't work if your starting simulation didn't already have output turned on. So if you had forgotten to click on the camera icon in your original simulation, this check mark won't do anything. CC3D installer, you shouldn't have to do anything with. And then there's this display command button. What that gives you is the full command line argument for running this simulation. And that can be a handy thing to save. So I'm going to come back over here and save it. That's a very long line. It goes on and on and on and on. And it's got the output directory switch or parameter, the install dir, et cetera, et cetera, et cetera. Nice thing to save because in the future you might want to run from the command line instead of launching it directly from inside Twitter. But this all looks okay if you want. And I'm also going to turn on to use the GUI, this one option. I'm going to hit run, cross my fingers. And at least it started, so there weren't any missing quote marks at least. It's going to do 2,000 simulations, or 2,000 MCS rather, sorry. Done. And there goes the next simulation. So it's just going to keep going. If you look at my command log window, so some of the text that I was building to write to the log file, I was also printing to the terminal. So we're also getting stuff written to the terminal. And there goes another run. Let's go see if we can find the outputs. So CC3 workspace. The folder called your simulation name with parameter scan added to the end of it. If you open that up, you get something like this. Every one of your simulations goes into its own folder. If you open up that, there's another folder. And if you open up that, that's your original simulation, your CC3D file, your simulation folder with all your stuff in it. So every one of your iterations will get this structure. This is part of the reason why it generates so much output. And we were writing to a log file. And that's what this log file is looking at right now. And this is not the interesting log file, because this is in that log file. So we're in one of these scan iteration folders. And you really don't want to have to go through each one of these folders and find that log file and collect them all up and append them or concatenate them. Or you want to do that. We want to do instead is go back to our original project file. Figure out which one it is. Let's see. Self-sorting base, P-scan right output. Output's not there. So I have a bug somewhere in, this guy's going to keep chewing its way. Well, it should be there. I'm just going to have trouble finding it, I guess. That's the workspace directory. Okay, we'll come back to that in a moment. So as you can see, this guy's keep chunking along. At least I don't have any crashes. Now, if you want, I'm going to skip ahead a little bit. So stopping it. How do I stop this guy? If you look at, I'm on a Windows machine, so if I look at my task manager, I've got several Pythons going. One of these Pythons is this particular running simulation, which you can see behind my task manager. The other Python is the pscan script itself. Some of these, if I kill them, no, I didn't. So you have to kill the right one. That looks like I killed the right one. No, maybe not. So we'll just kill them all. Yep. Which also killed my tweeted. Restart tweeted. Yep, that's got my parameter scan it. So that's how you stop it. It's not easy. Sometimes you have to do it several times. I've stopped it, but of course I still have all of my output folders. That's the workspace, the parameter scan. Now you see a whole bunch of them. We got up to the 17th iteration. I think we decided there were 18. So actually that was pretty close to being done. So I got all those parameter scans. Now obviously I had a bug because I'm not getting my log file written. So I want to run the parameter scan again after I make a correction. The problem is if I try to do that, go back here to Twedit and say open in player. All that stuff should be okay. Sure, turn the GUI on, tell it to run. So it won't start. In particular, it's this message here. Because this particular simulation of parameter scan was already processed. If you want to proceed, make sure to delete the workspace folders. So as far as the parameter scan tool is concerned, that scan finished, which means it actually did do all of the requested scans, even though I didn't get all of our output. But as far as it's concerned, it's done, and it will not let you run another scan. And it's using this directory, the existence of this directory, to tell it that the scan is done. It basically, when I tried to relaunch it, it opened up this guy. It found that this guy existed, looked in this JSON file, said, I've done everything I'm supposed to do, I'm done. And it won't let you start again. If you stop your parameter scan and it's not finished, and you reissue the parameter scan command, it'll restart at the proper place and continue on wherever it was interrupted before. So the pscan is pretty smart. It knows where to pick up if it's restarting, and it knows if it's done, and it shouldn't do anything else. So if you want to run another parameter scan, you have to do something with this entire output directory, this entire base parameter scan output directory. And the easiest thing to do is just give it a different name. Now, the parameter scan script and CompStyle player can no longer find this directory. But we haven't deleted the data. We still got it all. It just, the system no longer knows it's there. Now, if I relaunch the parameter scan, it'll start up at the beginning and go through everything. I just wanted to take a real quick look at what I did wrong here in my Python, so it's not writing that thing. Let's see. This is our new file. We'll open it as file 2. This is one of the reasons why you don't want to actually do a pscan until you're absolutely sure all your code works, because it's this process of making any kind of a change in the code and then rewriting it is much more tedious, because you've got all these pscan files you have to deal with. And the fact that as soon as you hit run, it's going to go off and try to do, in this case, 18 simulations. I just want the first one to see if I fixed my file writing error. Now, this here looks okay. So just as before, we got the path to the source, went up a dir, added a log, a name for the file, and opened it. Append. We wrote a line to it just for the hell of it. Self file 2. And down here, we wrote outline. It should be in the original project directory. Right, there it is. That's the right one, and I don't quite know. So this is my working directory, not the workspace directory, but where my project actually lives. And it did go ahead and write this file. And the file was opened for append. And I got my start. I was writing a timestamp, so that's a timestamp. So under the runtime column, and this I think is from an old run. But I don't see the error. Well, so this file should have had 2 lines for every simulation. It repeats the header every run. And then the timestamp, the value of the 3 values that were being changed, which were a little bit different than here. and then the hetero surface area. So at the end of the parameter scan, you would have all your parameters that you were changing and your final metric. Actually, what I'll do, let's try this. Right, this is the one that I had done previously, the solved example. We'll see if this one works. I don't know why it's popping this window up in the wrong place, but turn on the GUI and go, tell it to go. This project has a different name, so it won't clash with the parameter scan output in the workspace directory. So it's chewing along. But it's still not writing my parameters. That's okay. I'll have to debug it later. He's putting it somewhere. But so that's pscan in a nutshell. So again, a little bit of summary. So there's a slide here talking about how to stop a scan. If you restart a scan that hasn't finished, they'll pick up where it should. If you want to restart from the very beginning, you need to hide or delete that workspace parameter scan folder, and that'll let you rerun from scratch. If you are working on a Linux system, you can take that command that I had copied and pasted up here. It was in the other folder, the pscan run command, and wrap it in a script and put a no hop before and an ampersand after, and you can launch that as a command line and then close your window and it'll just run in the background. You can log off as well and it'll just keep running it. You can also take that Linux command and submit it 5 times or however many times you want. And the pscan script will take care of making sure none of those simulations clash with each other. It'll keep track of what the next simulation will do, and it'll start up however many pscans you launch. The first one will do the first parameter set, the second one will be doing the second parameter, the third one will be doing the third parameter set. But you can have as many pscans going as you want, all working on the same project, and they'll avoid each other and actually just do everything in order and usually behave quite nicely. But you need something like a Linux system where you can do a batch submission and do multiple batch submissions. Okay, that's pscan. When you get the output working correctly, I clearly have a bug in my output somewhere. That log file, I was writing something that looks like this. So there's a header line that just gets repeated every time, and then the value of the 3 parameters are being changed and my output metric. And you just take that table and put it in Excel and sort it, and that'll put all the headers together, and you delete all of them but one and get a nice clean table. And now a nice clean table. This table is sorted by the hetero surface or metric area increasing. Basically, the simulation is trying to minimize this number. And this is a graph. The blue line is in order, the hetero surface area in the order the simulation was run. The orange line is if you sort them by how the hetero surface area, how good the simulation did. you get, so obviously here's our best one, which actually turns out to be like this simulation here, or one of these two here. So that's kind of the process you would go through. You'd finally do it after you did your run. You're going to take your log file and do some further analysis of it. Okay, another handy thing to do with pscan is replicate runs. As you know, CompSol is stochastic, so every simulation, unless you set the random number seeds, every simulation will be different. So a parameter scan is a real easy way to do replicates. I'm going to see if I can kill my pscan here. There it is. So how would you do replicates? Well, replicates are, well, I didn't get to pscan. He's still going in the background. There he goes again. I missed the one I needed to kill. So it's the exact same approach, except you're just going to make up some dummy variable in, for instance, your Python, called replicate count. And originally in the Python, this is just replicate count equals 1 or whatever number you want. Click on it and add it to the parameter scan, and just tell it to do 3 replicates. Start at 1, go to 3, do 3 steps. I grab over here. So start at 1, and it's going to do 3 steps. So now if you do this with other parameter scan values, it'll just do every one of those simulations. It'll just do 3 iteration or 3 replicates of that same simulation. And just bang through them all by itself without any help from you. Again, if your simulation takes 12 hours and you want to do 5 simulations, you can actually, and you have the CPU power, or you have a cluster, you can go ahead and launch 5 separate versions of the pscan, and each one will be working on its one replicate, or we'll do 2 replicates, or however many the numbers work out to be. And then, just as before, you can write your replicate count into your log file, which is you move that tag around anywhere. So Pedro's got a good idea, and you can put that number into the seed. The nice thing about doing it that way is if you run the simulation again, you'll get the same results. Each simulation will be different, but if you run the entire parameter scan again, your first simulation, the second time you do it will match the first simulation the first time you do it. An interesting idea. So again, you can use this curly bracket parameter name anywhere you want in any of the files you want, the XMLs or the Pythons. The other thing about, so what Pedro's saying in the chat is, the other thing is when you're done, if you're using these values as your random number seed, you could say, I really like simulation 3. You can rerun that exact simulation. So you could turn on more output, you could save more screenshots, you could do a whole bunch of stuff to it. And it would reproduce that run that you had done in the pscan because you're using the same random number seed. However, right now, CompSol seems to have some troubles with its random number seed. So that may or may not work, but it's a good idea that you replicate it with more detail. How are we doing on time? We have a little bit more time. So if you get some time, try some pscans. Like I said, it's pretty easy to set up. If you want to remove it, it's more work. Here. Basically, you have to go through all your files and get rid of all those curly brackets. You can highlight it, a curly, and tweet it. You can highlight one of those curly brackets pair, right click, and there's a, just like there was add to pscan, there's a remove from the pscan. And it will remove your value from the pscan. Get back, they'll show you a little bit about getting rid of a pscan, how much work it is, and why I said make sure you fork the project and it works before you start, because getting rid of a pscan is not easy. So this has got the P-scan edit. So like I say, you can highlight it again, right click, and now you got remove from P-scan. Removed it over there in the JSON. Come back here and it put the original value back in. So you go through and you do all those. But then you need to remove this resource. Right click on it, remove resource. And it'll get rid of the P-scan. I'm not going to do it. But you have to make sure you find all of these occurrences everywhere. And I not only did I have them here, but I also had them in my output routine where they're being printed. They don't show up there. Maybe they get saved. So it's a pain to get rid of them, but it can be done if you absolutely have to. So parameter scans can be a good way of doing scans. You can do replicate runs for it. There's just a lot of really handy things you can do with a P-scan. As long as you don't let it get out of control and try to do 8 million simulations. Okay. Is there any questions anybody want to ask about that's the stuff so far? Transferring from 2D to 3D. I was going to talk about that a little bit later. It would be, it's hard to go from 2D to 3D. Some things are pretty obvious how you convert from one to the other, but some things are not nearly as obvious. What I would use a 2D for is just getting the bugs out of the code. Making sure everything runs, make sure there's no errors, make sure it's writing whatever information you want to files. And then when you go to 3D, that's a relatively minor change in the code. It may be quite significant changes in the parameter set. Like I say, some things are kind of obvious. You know, my cell was 10 by 10 in 2D. Well, it's going to be 10 by 10 by 10 in 3D. But the adhesion energy doesn't quite scale the same way because now you've got your perimeter now comes to surface and it's 10 times bigger. And how that interacts with your J values and everything else is not nearly as obvious. So in general, in a big simulation in 3D, what I'd use P-scan for is doing replicate runs. Parameter sweeps, do it on a cluster where you can launch 10 jobs across 10 nodes or something like that. Oh, excuse me, trouble with my voice. Okay, let's see what other questions we got. Okay, can you change two values together? Well, you could certainly put a Python command that said, you could do something like, right? You could put them into any mathematical formula you want. So you could have some value that's the product or the ratio or the sum or anything else you want. You put any kind of mathematical equation you want. This when the parameter scan gets run, this is just going to be replaced with the numerical value. So this is perfectly valid mathematics. Because by the time the Python interpreter sees it, it won't be curly bracket JCAM. It'll be some numerical value. So you can do that. Do any kind of mathematics on it you want. What you can't do easily is something along the lines of, I'm going to run 10 simulations and look at my results and then change the future values that I was planning on doing. If you're really good at programming, you might actually be able to do that, but it would be really tricky because you'd be trying to do something like edit this JSON file on the fly. It might be doable, but in general, that's probably beyond the capabilities of a PScan. Though there might be another way of doing it. You could certainly have the PScan just doing iterations. You just tell it to do, or not iterations, replicates. You just tell it to do 100 replicates. And you could have the Python open your log file from the previous runs and make a decision about what it's going to do next in terms of parameters. And that little piece of Python, that chunk of Python code is what would set your parameters. TJ will talk about it later, I think, and it's probably better to do it the way TJ will say, but you could write this as an optimizer. The PScan would just, you're going to do 100 steps to do an optimization, and it's just going to keep looking back at the previous log file to see what to do next. Did my error metric get better or worse? Which way? What do I think the derivatives of the variables are, and all that kind of things. To make files. So if you want to, for instance, in that simulation we were running, there was that graph, the plot window. So yeah, you could write into your Python, instead of writing just the log file, you could write the data from that graph. So you'd get every run would give you a log file, and every one would give you a separate file that's just comma or tab separated X and Y values, or X, Y, and Z values, whatever you think you want. You could also write, again, all the graph information into one big file, just appending it with a column that's the run ID. So the first column in a row is the run ID, and then you've got your X and Y values. And your log file just has all of those rows in it. In Excel or something like that, so you pick run 5 and just take all the lines that start with run 5. That would be your data. So absolutely, you could save any graph data that you wanted to. Yeah, and then you could write another Python script to write it. If you really want to, I mean, in CompuCell, you can add or load matplotlib, and then use matplotlib to generate a graph, and then save the JPEG or whatever you want image of that graph. It's a nice, pretty matplotlib image. I think in general, I would do extensive graphing outside of your CompuCell run. You could do it in the CompuCell, but I would, save your data and tackle that as a separate problem. Yeah, TJ will also talk about Python and Slurm and things like that. I've run this PScan on a Linux cluster with Slurm and run, using 250 processors and running 50 jobs simultaneously on a PScan that was going to do 10,000 simulations. It can be done. If you really need to do it, it can be done. Okay, before we get completely out of time, we only got about 10-ish minutes left, I think. This is just some thoughts about things. I'm going to change the screen share. Just my PowerPoint. So we're done with parameter scan. All the slides, the slide deck is shared if you want to go back and get some more detail. There's the replicates. There's just a slide here that lists all my demos. I'm very excited. A little bit of a quick discussion on some best practices. There's a lot of things that you can discuss in best practices. Hopefully I'll give you some ideas about kind of help you keep things sort of clean without getting so complicated that it makes it difficult to actually make progress. We had the question about this before, 2D versus 3D models. Think long and hard before you do a 3D model. Because if you just think of my model 300 by 300 by 300, and you compare that to 300 by 300 by 1, the 3D model is 300 times slower. As a first approximation. That's a lot. Your 1 hour simulation goes to 300 hours. That's a non-starter. You can do an awful lot of stuff in 2D. Always try to do a 2D model. Even if you're absolutely positively sure eventually you're going to be doing it in 3D, still start with 2D, because you're going to want to run 10,000 Monte Carlo steps to make sure that your close function doesn't crash. And you don't want to have to wait 3 days to get your finish function to run once so that you can find out that it's going to crash. So even if it's got to be 3D, start in 2D and convert it once you get everything worked out, figure out what you're trying to do, got all your fields set up and everything else is ready to go. So first best practice, do it in 2D if you can get away with it. You'd be surprised what you can get away with in 2D. Second best practice, write a biological description. James talked about this in his very first seminar way back, the Tuesdays back. Keep a running file of what you think your biology is. It can be a Word document, it can be a PowerPoint, anything that you feel comfortable doing. It's nice to do it in something like Word because you can include pictures and drawings and a lot of other stuff, as opposed to a plain text file where you just have words. And just keep very simple lists of, these are my biological entities. I've got 3 cell types and I've got 1 diffusing molecule, and that's all that's in my model. But you should have that explicitly written out somewhere. And then a list of the processes. Processes are things that change your fundamental physical things. So I've got diffusion in the model, I've got cell death or division, or whatever. Just a list of those. I've got cell type A, it proliferates. I got cell type B, it doesn't do anything, it just hangs out. I got cell type C, it dies. Just those lists of those things. It'll be very handy if you ever get to the point of writing a paper, because that's really what people want to see first, is just what are your cells? What are your cells and what do they do? It'd be nice to have citations to all those things. And if you do it, like I say, if you do it as a Word document, you can just evolve it as time goes on. And you can keep this Word document in your copy yourself folder with your project. So here's, I don't have the screen share set up for it, but in your top level simulation folder, just have a Word document that describes that project, what you're trying to do in that particular version. So keep a biological description around. Very good idea. Best practice for project file versioning and tracking. If you're a programmer, you're just wonderful with GitHub and SourceForge. In my experience, people that are not programmers, they look at GitHub and SourceForge and they can't figure out what the heck's going on. It makes absolutely no sense at all. It doesn't have any best practices. It's just, here's a bunch of stuff you can do, figure out what you're going to do. Advantages, programmers love it, and it keeps versions and it's wonderful. Disadvantages, it'll take you 2 weeks to figure out what to do with it. So that's GitHub or something like that. So second way of doing it, okay, just keep it in a Google Drive or a Dropbox. That lets you share it. And actually a Google Drive or Dropbox versions. Every time you change that file, there's an old version saved. So you can roll back in versions. Requires internet access. Cost may be an issue. All kinds of reasons you might not want to do Google Drive. Finally, just keep copies of your project folder. Every day, make a copy of it, put the timestamp on it, date, and we'll put a date name on it, make a copy of the file and keep it. If you're keeping a Word document of your biological descriptions, every time you version it, that guy just carries along with it. And you've always got the biological description you used for the version you did 3 weeks ago. And you know what was in that version 3 weeks ago. This works perfectly fine. It's much simpler. It's hard to share things, but this is the minimum. Every day, every week, just version your folder, keep the old folder around. Yeah, so that's just keep a local file. Make copies of your project directory every so often. Where I'm lost where I am with everything. Parameters. Keep track of your parameters. The worst case is your parameters are not specified anywhere. They're scattered all over the files. You've got the volume, target volume of cell type A in 2 different places. and you decide to change it and you forget you've got it in two places and you just change it in one place and not the other. And now you got a big problem, right? You assign the cell volume, target volume in the start, but you've got mitosis and you did cell division. And you forgot to change it in the cell division code where you get a new cell and you have to reassign its cell target volume. So keep track of your parameters. We'll talk about it in a minute of how to do that, but in addition with your parameters, keep track of their units. How do you do this? Easiest way to do it, and it would actually be nice if CompuCell made a template. When you made a new project at the top of the Python file, it would just do something like say, what is your conversion from seconds to MCS? You should write that at the top of your Python file in a comment. And if you don't know what that should be, just put 1. I'm saying an MCS is 1 second, or an MCS is 1 minute, or it's 1 hour, whatever you think is appropriate. Really doesn't matter. The point is to have it written down somewhere so that in the future, you can remember what your assumptions were. You can certainly go back and change it, not a problem. Put your assumption explicit somewhere. The same thing with microns to pixels. How big is a pixel? By default, a pixel is 1 micron. Fine. Write it down. Write it down. Even if it's just in a comment at the top of the file, write it down. How big is your model? You may say, well, it's 200 pixels wide. Great. How many cells is that? Because that's actually biologically what's relevant, is how many cells wide is your model, not how many pixels wide. Pixels wide is computational detail. How many cells wide is your, write that stuff down somewhere. Even if it's just in a comment, that's better than nothing. There's better ways of doing it, is make a parameter file. And you put all kinds of stuff into a parameter file. So in CompuCell, I don't want to do it that way. Let me find the right side. So here's a Twedit window. You can right click over here and add a resource. And in the dialog, you give it a name, maybe call it parameters, tell it it's a Python file. Finish. And now you have a new file in your simulation called parameters.py. And that's a great place to keep all this information. So, version number, date, who did it. And here I've got model width in cells equals 10. The cell width is 10. And my pixels per micron is this. It's all written down. It's all explicit. I can do things like say, I want the model to be 10 cells wide. But for speed, I'm going to set the cell width to be 2. So my cells are 2 by 2, so my model's only 20 pixels wide. For debugging, the thing will run just blazingly fast. And then when I got all my code debugged, I go back and say, well, I want a reasonable size in pixels for myself, so I'll make it 20 by 20. Now my simulation is, whatever it is, 200 times slower. But all I do is I change it here. And I've got everything noted, microns for pixels and everything like that. This file, this parameters.py, you can just import into every one of your files. So here's a Python only simulation, and I do import parameters as P. And when I define my model width, I use p.modelWidthPixels and p.modelWidthPixels. And those are 2 values that were in that parameter file. And if I make a change to my model width, it automatically propagates into all these files downstream of it. Plus, if someone asks me, what's the model width in pixels, I know it only occurs in one place. It only occurs in the parameters. And if I look at my parameters file, I can have a note saying a pixel is 1 micron or half micron or 5 microns or whatever it happens to be. So make a parameters file. It's a great way to keep track of your parameters. The file can be as complicated as you want. Right here, I've got model width in microns equals 10. I've got, I say my units are microns. It's a comment, and there's some citation. There's PubMed ID. I don't know why I've used a paper reference in my model width, but certainly if I had a parameter that's volume of a cell, I might want to cite where that came from. So this is a great way. It's a simple way of keeping track of all your stuff. I recommend doing it. Even if you're not going to use the parameters file to actually keep values, to make a parameters file and just make it one big text string. and keep track of your notes. Write your notes. What's your pixel resolution and things like that. There are some slides in here. Somebody had asked about 2D and 3D. There's some slides in here about converting between 2D and 3D and how adhesion values and lambdas thing. You can take a look at those if you're interested. There are some ways to go 2D to 3D, but it can be pretty tricky. Also in here and along with the demos, I use this process here, this parameter process, to set up a simulation that's self-sorting that lets you, just by changing this one parameter, pixels per micron, do the exact same simulation, the exact same number of cells that are 40 by 40 pixels, 100 by 100 pixels, 200 by 200 pixels. So this might be the one you want to do ultimately, but this one's much, much faster and lets you do all your debugging. The other nice thing about this approach is that if you think about pixels per cell, you know just intuitively that if you make it a 2 by 2 cell, it's going to behave a little weird. And you might need 10 by 10 or 20 by 20 or 100 by 100. The question is, how big does it have to be to behave correctly? Well, if you've got it set up right, you can change one parameter and do a simulation and then just plot output versus resolution. And you'll find that the simulation behaves differently up to a point as you increase the resolution. Eventually you get to a resolution where making the pixels smaller and smaller and smaller no longer makes any difference at all, other than the fact that the simulation gets slower and slower and slower. But you've actually directly addressed the issue of does pixel resolution affect the outcome of the model. So that's another advantage of having all of your parameters pulled out into a single place where you can deal with it better. That's rescaling. Again, another thing about having that parameter file is when you version your file, you've got all your parameters saved because they're in that version of the file. I'll skip this. This is something I've been trying to convince TJ to do for a long time, but basically make a data type, a class that's a parameter. And the class parameter would have, so I'm not going to skip it, I'm going to describe it. The class parameter, you make a parameter that's called cell width, and it automatically has slots for a numerical value, for a unit, and for a reference. So a parameter becomes a Python class that has a particular structure to it. Okay. James made a comment about adding standards. Yes, it's something we've been talking about for a while, and we can certainly do better. And he's also added a reference about 2D to 3D and a site for it. So I would argue you still always start in 2D because you've got a lot of coding to do and a lot of bugs and foibles and things you need to discover. Is there any other questions? I'm a few minutes over. All my slides are in the share, or the slide deck is in the share, and all those simulations are in the share as well. I'm sorry I couldn't get the pscan to log to the file, but I think you get the idea that it's doable. You just have to make sure you get all your code tweaked properly. So at the end of the pscan, you have a nice clean table that you can actually analyze. To Mango, yes, absolutely. And that would be part of having a specific class for a model parameter. So you can assign units to the variable. And, you could do it kind of loosey-goosey and let anybody put in anything they want, misspell micrometers or micrometers, which is what I'd most certainly do. But it'd be even better if you had a little tool that said, okay, you're going to create a new variable, and a window would pop up and twet it. And it'd say, is it, an int or a float or a string? Pick one. And it says, what are the units? And it has a drop down, and it has the ontologically defined biological units. organized into here's all the lengths, here's all the volumes, here's density, so that you're actually using a proper ontological tag. And then if you're saying, well, a citation, the unit, the value, to be able to say things like this value is for 2D and not for 3D, or vice versa. Diffusion constants change in 2D versus 3D. And that also be able to extend the same idea to your cell types. You created a new cell. Well, tell us what that cell is. And again, have a pop-up that says, let's go to the gene ontology or the cell ontology and find, vascular epithelial cell. And you might call it epicell in the simulation, but in your annotations, you'd have, well, epi means cell ontology, such and such and such, whatever their official name is. That starts to let you think about doing things like mining models and saying, well, let's find all the epithelial models without having to go to the literature, but actually just looking at a repository of models. As it is now, I would call it an epi, somebody else might call it an epicell, somebody might call it an e-cell. There'd be no way you could search through code, but we should be able to fix that without too much trouble.